The next problems that open loop control systems have are regarding tracking and robustness. So over here, again, we have the open loop control system shown in the form of block diagram. If we define the error term E as the difference between R and C, so error is equal to R reference minus C, the actual output, then we will get this expression here. So 1 minus GCOL times GP times R of S minus D of S. Now, if we assume that we have a constant known disturbance, which is shown as D bar, and we have a constant reference R bar, then it is possible to find out the steady state value for the error. So we have limit of E of t as t goes towards infinity, which is equal to limit of S times E of S as S goes towards 0. And then if we replace R and D by their equivalent Laplace transform form, so R bar over S and D bar over S, and since we are considering the steady state case, for the controller we assume that we have K as the DC gain. Then we will obtain the error term in the steady state being equal to 1 minus K times GP at 0 times R bar minus D bar. And obviously we want to have it equal to 0. Out of that we can obtain the value for K, which is K equal to R bar minus D bar over GP bar times R bar. So if we set the DC gain of the open loop controller to this value, then we will have the steady state error equal to 0. For the special case when D bar is equal to 0, K will be obtained as 1 minus GP at 0, which is similar to what we just obtained in the previous slide. However, you should keep in mind that in real situations, we are completely unaware of the disturbance. So we don't know even when the disturbance is going to happen, and we don't know the value that we have for the disturbance. Even if it happens in the form of a step, we don't know the amplitude for that step. So we don't have enough information regarding the disturbance, and as a result, the assumption that we make here will not be valid. And therefore the open loop control system doesn't have the robustness. There is no robustness because if the disturbance happens, the control system will not do anything. It is just directly being added to the output of the plant. The next thing is regarding the sensitivity. If for now we neglect the presence of D and assume that the plant has a nominal DC gain of GP0 as before, again here pay attention to the word nominal DC gain, then in practice the DC gain will not be exactly the same as what we have assumed. So GP bar is the nominal value, but the practical one will be GP bar plus delta GP bar. This delta GP bar will be a small amount usually, but it will be a variation compared to the nominal value. And it might happen because there are some internal parameters which are different than the nominal values that we have assumed for them. The nominal DC gain of the open loop system, L bar, which is defined as L evaluated at 0, for which we have L equal to C over R, obviously, and then it is equal to GC open loop times GP. If we find out the nominal value for this, the nominal value for the DC gain of the open loop system will be equal to GC bar, and we can replace it with GCOL bar with K times GP bar, or K times GP bar. This is the nominal value that we have for L bar. And then the practical value for it could be obtained as, you can see here, L plus delta L bar, which is obtained as K times GP bar plus delta GP bar. This is the variation that we have for the DC gain of the plant. And it will give us at the end L bar plus K times delta GP bar. In other words, delta L bar is equal to K times delta GP bar. And you can see it over here as well. So K times delta GP bar is what we get for the variation in the DC gain of the open loop control system. Now we define the sensitivity of the open loop system, as you can see here. So S bar OL for open loop is defined as delta L bar over L bar over delta GP bar over GP bar. And it's indeed the ratio of the fractional change delta L bar over L bar to the fractional change of delta GP bar over GP bar. And if we now replace delta L bar with what we obtained here, K times delta GP bar, we will end up with delta L bar over L bar times GP bar over delta GP bar. And for L bar, we also have the expression K times GP bar. Therefore, we will get open loop sensitivity for this system being equal to 1. So this is quite important to keep in mind. The sensitivity of the open loop control system is equal to 1. It means that any fractional change in GP bar causes the same fractional change in L bar. And this is not a desired behavior, because we want our control system to be less sensitive, let's say, to the changes that we might have in the plant. In the ideal case, it should be equal to 0. And this is the worst case. So this is what we get with the open loop controllers is not desirable in terms of the sensitivity as well. Here we are going to have a look at the DC motor example that we had regarding the open loop control. So here you can see a graph which is indeed showing you the step response of the system, where we have the open loop control system for the nominal model with no load torque. So there is no disturbance and our model is nominal. So we have no disturbances. The parameters are exactly as in the model, so there are not variations. Let's say we are using the nominal values for the DC gain of the system as well. The performance is shown here. It is, let's say, good. There is no steady state error because the final value that you can see here is equal to 1. So this is the unity step response, and therefore the steady state value is 0. There are some other properties that we will discuss later, but for now we can say that this is a good response. However, if we assume that we are in the real life case and there are indeed disturbances happening, over here you will see how the behavior of the system will look like. So we assume that a constant load torque dH of minus 0.025 newtons starts acting after 2 seconds and acts on the system as the output of block HP. So it is indeed being added to the output. So we have GC, GP, and here we have the disturbance. It happens at this moment, 2 seconds. So until that 2 seconds, you can see that the output is basically the same as what we had in the previous slide, but right at that moment when the disturbance happens, you see that the behavior of the system changes. Instead of reaching 1 at the steady state case, the output goes down and it reaches 0.775, somewhere like that, yeah. And therefore we will have this steady state error. The steady state error will not be equal to 0. So this is the case when we have the disturbance. The second case is regarding the changes in terms of the parameters of the system, where the DC gain of the system is not the same as the nominal one that we had. So we know that, or it is known that the armature resistance in electrical motors increases as the temperature increases. So as you use the motor, the temperature increases, or as the temperature of the environment changes, the resistance of the armature of the motor, of the electrical motor that we are discussing, will change. In the extreme cases, it can become twice the nominal value. Over here in the graph, you can see what happens if there's no load. So here, no torque. Indeed, we don't have the disturbance, let's say. No disturbance. But the resistance of the armature of the robot is 20% larger than its nominal value. In terms of the shape of the response, we can say that it is similar to the case where there is no disturbance and there is no change in the parameters of the system, so what we have here. But you can see that the final value is not equal to 1, so we have steady state error. So if anything changes in the plant, in any parameter in the plant changes, we will not have the zero steady state error as we expect. Alright, in the next video I will go through this example and then we will finish this lecture.